Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 9 and we will be looking into basic MOSFET structure, its symbol and then its basic working principle as a switch. So, these are the areas in which we will be looking into as far as this lecture is concerned. So, the outline of the talk is we will give you a brief introduction of MOSFET, basic structure, MOSFET operation principles, IV characteristics, and then application of MOSFET as a switch, and then conclusion and feature scope. Why MOSFETs are studied? Because these have been the workhorse of semiconductor industry for last so many decades. In fact, Edgar Leinenfeld had a patent which was in 1925 to 27, in which he gave this concept of MOSFET, the field effect transistor. And it has been a long growth after that, about a century of MOSFET, where the concepts of having that the field can actually influence the current and field can modulate the current, and by application of a voltage therefore I can modulate a current, was first done in a MOSFET. And this has been used both in analog design, in digital design, in mixed signal design, everywhere it is being used to a larger extent. And not only that, it has also been used for as a switches also. So, we will go one by one and I will go a bit quickly in this case because there are many good lectures available already to you in NPTEL and otherwise, where the basic building block is already discussed with you in a detailed manner. So, let us go to introduction to MOSFET. As you all know, MOSFET stands for metal oxide semiconductor field effect transistor. So, it is basically MOS. So, that is the reason it is MOS, MOS, and then you have this field effect transistor. Field effect transistor, I hope all of you are aware of, that the field is affecting the charge carrier movement within the channel. And why MOS, we will come to that in the next slide, right. It is one of the most fundamental component of modern electronics for sure, and it can be used both as a switch as an amplifier. So, when you talk of amplifier, this is where we talk about analog domain, and we can use an analog signal to amplify an analog signal and get the output. Switches are generally used for digital logic, right. For digital logic it is used. So, both the applications where you use digital logic or analog logic, this MOSFET is well defined structure and well defined device which has been there. There are two types of devices in MOSFET, one is an N channel, another is P channel. N channel is where the electrons are basically the majority carriers and they carry the current from source to drain, and P channel is basically having P type semiconductor, right, or a P type holes be the carrier. So, for an N channel, the carriers are basically electrons, and for P channel the carriers are effectively holes, right, and this is what is known as electrons and holes they will carry, right. This is one thing. So, they are segregated by looking at the type of carriers which are responsible for the flow of current. Another type of MOSFET which people generally follow is, and maybe we will show it in the next slide, but here I can give you a brief insight. So, I will just give you a brief insight here, is known as an enhancement mode MOSFET, and you have a depletion mode MOSFET. So, depletion again N and P, and enhancement also N and P. So, typically you can have 4 types of MOSFETs generally available, which is segregated in terms of its carrier and in terms of its operation, right. We will come to this one as we move along, but therefore, effectively you can have 4 types of MOSFETs available to you. This is the basic structure of, let me say, an enhancement mode MOSFET or any MOSFET here. If you look, it is basically a 3-terminal device, though it is actually many people have shown it to be as a 4-terminal. But the first thing which is noticed to you is a 3-terminal device. What are the 3 terminals there where the biases can be applied? One is source, right, one is gate and another is drain. So, these are the 3 main sort of biases. And if you look at this black colored, these are basically your contacts, these are metal contacts, right. And this is the drain here, this is source, and then this is the gate contact, and then what happens is just below the gate you have silicon dioxide. So, this light blue colored is silicon dioxide, and then you have the substrate which is P type substrate here. Now, let us go one by one to see what is the doping concentration. This is a P type substrate, which typically means this is also referred to as a body. So, you will learn later on that you can also have a 4th terminal which is the body terminal, right. At this stage we will not go into details of that, but we will keep restricted ourselves to a 3 terminal device, which is basically source, gate and drain. So, basically source to a larger extent in most of the cases it is grounded. So, what I have shown you here is the source where you apply a voltage Vs is basically grounded. Drain, we are applying a voltage Vd, and on the gate side we are applying a voltage Vg. These are all DC biases currently, and these are fixed DC voltages which is being applied at this stage. However, within the source, so this is source contact and drain contact, and this is this sort of hyperbolic or this part is basically the source, drain and the source, and source and drain, they are highly doped. So, you have, and that is the reason it is written as N plus, they are very highly doped, right. And so if you look very interestingly, this is the width of the device, right, and this is the length, right. Length is defined as from the source to the drain is defined as the length. So, source to drain is defined as the length of the device, right. Ideally, if I do not do anything else and everything else is common, then the gate length, the gate length is this much is the gate length, right. This is the gate length, and the channel length capital L, they match with each other, right, and these are known as self aligned structures in a sense. Assuming that they are matching here, they are not here, but if you look very carefully, if this is the source and this is the drain here, this is source and this is drain, then you will see this is the oxide layer here in this phase, and then you have this metal layer coming here, right, MO, and this semiconductor. So, that is the reason it is a metal oxide semiconductor. This is N plus, this is N plus, this is metal and this is oxide layer. Now, you see they are perfectly aligned with respect to each other in the source drain region here as well as here. Here you have some overlap. At this stage it does not matter, but the functionality does not affect too much, but it influences the performance parameter in later stage. This W is referred to as the width, right, and this L is referred to as the channel length. So, width divided by channel length is referred to as the aspect ratio, defined as the aspect ratio, correct. We will see it is working maybe after some time, but this is the overall structure where you give a positive bias. If it is a p type substrate, you give a positive bias on the gate side and you give a positive bias on the drain side, and you ground the source terminal, right. At this stage, let us not go into the principle of working. Look at the structure and understand the biases here. I am not giving any bias on the fourth terminal of the device. Now, so we knew this is a 3 terminal device, and therefore there can be, as I told you also, there will be a fourth terminal which is the body terminal here. Let us just concentrate on NMOS here, this and this. So, there are in fact 3 ways of showing the symbols. The first symbol is the most widely used across the network, and this is this one. So, if you put a bubble in front of the gate, that is PMOS. If you do not put any bubble, that is NMOS, right. Similarly, if there is an arrowhead which is going towards the source side, then it is an NMOS. Any arrowhead which is coming from the source side is basically your hole. The direction of the arrowhead is primarily the direction of the holes. So, if you apply a positive bias here, right, and let us suppose this is grounded, then if it is an N channel device, electrons will be flowing in this direction. So, the conventional current will be flowing in this direction, and that is the reason the arrowhead is from drain to source. Whereas, if you look at PMOS, holes will be moving, and holes will be moving from where to where? Source to drain, right, because drain you will apply a negative bias, holes will be attracted towards drains, the arrowhead is from source into the drain. So, that is the reason the arrowhead has got a meaning. That arrowhead actually tells you whether it is an NMOS or PMOS. And if you look at bulk, then the bulk is shown either by a dotted line, and this dotted line shows you it is connected to the body or bulk, right. There are many parlance available. One is known as a substrate, another is known as body for B, source, drain, G. So, this is basically we are looking into 4 terminal device. For all practical purposes, maybe we will be sticking to this sort of notation or symbol for this course, right, and the symbol is very straightforward. This, right, is for NMOS and this for PMOS, that is all, right, where this is the drain source. Obviously, they can be interchanged, and this is the gate, and this is the drain, source and the gate. Obviously, you can understand which side is which one, right. So, this is the MOSFET symbol which we are using. As I discussed with you, there are 2 types of MOSFETs. One is a depletion type MOSFET, another is enhancement mode MOSFET. Let us come to enhancement mode MOSFET. These MOSFET are normally off devices. Normally off means if you do not apply any bias, there will be no current flow, right. And moreover, even if you apply a bias on the drain side, right, you have to apply a positive bias on the gate side for a current to flow. So therefore, they are also referred to as a normally off device, enhancement mode. These are normally off enhancement mode, and therefore you have to apply an external bias to switch it on. Whereas depletion mode, they are normally on devices and you have to apply a bias to switch it off, right. So as you can see from the write up here, depletion mode MOSFETs are normally closed devices, whereas enhanced devices are normally open switches. Normally closed, why? Because they are anyway closed, right, because even if you do not apply a bias, or even if you apply a bias, there will be always a current flowing there. I will tell you why later on. At this stage, just understand this point, that normally closed and normally open. Normally closed basically means the device is on and the switch is closed. The source and drain are connected through the channel, whereas normally off devices are open and source and drain are not connected. So just keep these two concepts in mind. We will return back to its understanding later on. So let's go one by one and explain to you how MOSFET can work as a switch, right? How MOSFET can work as a switch, and I will use the formula later on, but let me come to this here. So we have understood this major point. Now let's see its working principle. The working principle is very simple and straightforward. You can find it in any of the books, large number of books, and it has been explained properly. But let me give you a brief insight so that will be enough for you to start with this lecture. See, if you assume that Vs equals to Vd equals to Vg equals to 0, then there is no bias voltages. If there are no bias voltages, there will be no current. That is, it's a trivial sort of information, because there is no bias, no electric field, no movement of charge carriers, and they will be there. Under no bias condition, this N plus with this P region and this N plus with this P region will actually form a depletion. So there will be a depletion. So this is N plus, this is P, this is N plus. You haven't applied any bias here. This is the gate and this is the drain and this is the source, let us suppose. You haven't applied this or this. Anyway, this is grounded, so it does not matter. So even under such a criteria, there will be a depletion region which will be something like this, right, which will be extending into the P region. And this depletion region will be basically, why? Because even under zero bias, there will be some electrons traveling towards the P side recombining, and therefore there will be depletion charge available. Now let's go one by one and see what happens. Let's see what happens if I go on increasing the value of Vg. Let us suppose this is 0.3 volts and this is grounded, let us suppose maybe. So there will be an electric field which will be directed in this domain, correct? Because of this electric field, electrons, or basically minority current carriers in this p-type semiconductor, will start moving up. One, there will be heavy injection from N plus region here and N plus region here, because there is a strong electric field present. It is so strong that it is even overriding over the depletion width, and as a result there will be a large carrier density of electrons available here. There will be electrons. Now understand, when you did not apply any bias and you made your gate voltage higher and higher, you are able to pull the electrons right from source, drain and the substrate. In the substrate, minority current carriers, source and drain already N plus regions are there, and you are able to pull the electrons near the silicon dioxide interface. Which is the silicon dioxide? This is your silicon dioxide, right, and this is your silicon. So you have, now what I will do, I will still go on increasing the gate voltage. What will happen is that now the holes which were initially here will be pushed here, and the electrons will be pulled up. So there will be again a p-n junction diode, and there will be also a depletion region which will be formed near the source, near the channel region. But please understand, since I haven't applied any drain bias at this stage, there will be no charge carrier flowing between source and drain. Though there is a large number of electrons which are available at this particular point, say let us suppose this particular point, there are large number of electrons available, but it is not helping me. So since this is a positive gate bias, right, you are basically forward biasing this distribution region will go on decreasing here. However, now if you apply a drain bias and then this drain bias is such that it is very large, this depletion thickness will increase, but this will also allow a large value of electric field to pull these electrons from here to here, and the current will flow. You got the idea? So the idea was that you form first a channel between source and drain, and then you apply a drain bias to pull the electrons towards the drain side, and that will generate a current, right. Now let me explain to you one term that is the most important term in MOSFET, and that is known as the threshold voltage. So what is the threshold voltage? Threshold voltage basically means that this channel, this is known as channel, has as many number of electrons per unit volume as there were number of holes available there. So let us suppose there were 10 holes available there because it was p-type semiconductor. If there were 10 holes per unit volume available to us, then as you go on increasing the gate voltage, first there will be a depletion region formed because the holes will be pushed backwards. Backwards means downwards, and therefore there will be no free charge carriers, there will be depletion region. And then as you go on increasing the gate voltage, more and more electric field increases, and now you will be able to pull the electrons near the interface. Now as you go on pulling it, keep in mind that when the number of electrons per unit volume becomes exactly equals to the number of holes per unit volume which was initially there, then I can safely say that gate voltage is defined as the threshold voltage. And this is the point where the device switches on if you apply appropriate drain bias. So coming back to therefore MOSFET as a switch here, so you see I have already discussed this point, that what is the threshold voltage of gate to source voltage. So which means that as the gate voltage crosses the threshold voltage is VTH, right. As the gate voltage is greater than equal to the threshold voltage, right, there is large number of electrons created in the channel, and therefore the resistance to the channel goes down and you can have a large amount of current available to you. Now which means that the gate is basically like a controlling factor between the current between the source and drain, and when the gate voltage is greater than threshold voltage, there will be some charges being accumulated. When it is less than threshold voltage, there will be no charge accumulated in that case. So that is what we get from that discussion here. Now so just look at these key questions, right, and try to yourself answer it from the knowledge you have gained till now. You will be able to do that very easily. For example, how does the resistance depend on the terminal voltages? Of course, as the gate voltage goes on increasing, you will have more and more number of charge carriers, and therefore the resistance will go on falling down and the current will increasing. Similarly, the drain voltage increases, the currents will increase. These are all very simple and straightforward, right. But what we can do is we can actually emulate this as a resistor here now. Why? Because its current is flowing, a voltage is given, V by I equals to R, and that R is basically the resistance of the channel, correct. It also takes into account the resistance of the contact, the source drain region, the depletion region, the channel, everything takes into account, and that gives you a lumped value of the resistances. So therefore I can use MOSFET as a switch. I can switch it on by applying a gate voltage greater than threshold voltage and a drain voltage, a positive drain voltage, and if you want to switch it off, I need to make my gate voltage less than threshold voltage. So VGS, and always we write down gate to source with respect to source. If it is less than threshold voltage, it is in the off state. If VGS is greater than equals to threshold voltage, this is in the on state, right. So these are the two states available for the MOS device. So these are the equations which people follow, and I am not deriving it in the class. You can get it in the standard books available, and the left hand side is for NMOSFET, and the right hand side is for PMOSFET. We will not go into details of PMOSFET at this stage. NMOSFET I will tell you what happens. As I discussed with you, when the gate to source voltage is less than the threshold voltage, there is no current and the device is in the off state, and we define that to be as a cutoff, right. So there is no current flow and gate to source voltage is less than the threshold voltage, and we come to know that therefore the drain current is exactly equals to 0. Let me come to a point where gate to source voltage is surely above the threshold voltage. So the first condition is met, right. However, my drain to source voltage is less than the gate to source minus VTN. This VGS minus VTN. VTN is the threshold voltage, right, and this is gate to source voltage. This is referred to as a overdrive. So when my drain to source voltage is less than my overdrive voltage, right, then my drain current equation comes out to be this. I will explain to you what Kn term is, but comes out to be this. And therefore if you see very interestingly, the current actually depends upon the value of VGS minus VTN, which is the overdrive. It also depends upon the drain to source voltage, but ID has a VDS square dependency. So in triode region, ID has a dependency as a VDS square, because if you multiply VDS inside, is square. So you can write it down here as VGS minus VTN into VDS minus VDS square by 2. and that's the reason you will see a non-linear region, linear, and then non-linear will come into picture. We will discuss that later on. Correct? What is Kn? Kn is given as mu n C oxide W by L. Kn is mu n C oxide W by L. Mu n is the mobility of the charge carriers, C ox is the oxide capacitance per unit area, and W by L is the aspect ratio. So this is the triode region, and then we come to the last part, and that is saturation, where the gate voltage is surely above the threshold voltage. The device is switched on, but my drain to source voltage has exceeded the overdrive, and then I get a current which is independent of VDS. You see, there is no VDS term coming into picture. It only depends upon VGS minus VT and whole square, which means that ID is independent of VDS, which effectively means that a constant current you will go on getting at a very large value of VDS, and it will be independent of the value of VDS. So let me come to the part where we discuss the values here. So I get, therefore, in the triode region, ID is proportional to VDS square. In saturation region, ID is independent of VDS, and this exactly the same nature is shown here, and we will discuss from here in the next turn, right. So we have learned about the basic MOSFET, its structure, its biases, and basically the three regions of operation of MOSFET at this stage. From next class onwards, we will look into the graph, ID/VD graph of a drain current versus drain voltage of a MOSFET enhancement mode, and we will move forward in this manner. Thank you.